Well, see, quantitative aspect of Faraday's law. So electrolysis has two aspects. First aspect I have discussed, qualitative, means preferential discharge of ions. Now see the quantitative aspect. So this quantitative aspect is covered in Faraday's two law. So first law is, see, first law. See, suppose that if you have an electrolytic cell like this, right, and you have anode and cathode, anode and cathode, like this arrangement. So what Faraday has observed, that suppose that we have taken A plus and B minus electrolyte. So B minus will move towards this anode and A plus move towards the cathode, right? So the amount of A plus and B minus deposited at the respective electrode and how much current is passing through this electrolytic solution or electrolyte, this, see. So there is a quantitative relation between mass of species deposited, mass of anion and cation deposited, or mass of species deposited, with the charge passing through this system. So if we are passing Q charge from this external source, external battery, we are passing through Q charge. So mass of deposit, mass of the species deposited is directly proportional to the Q, right? So this is the first quantitative relation between electrolysis, quantitative relation, quantitative aspect of electrolysis. What is the M here? M is the mass of species involved at the respective electrode, at the respective electrode, right? And Q is the charge. Q is equal to, you can write I into T. So Q is the charge passed through the solution, passed through the solution. And I is the current, and T is the time. So charge you can convert, so it is simple. So now proportionality sign, you can remove this and put some constant here. So M is equal to Z into Q. This is equation 3. Or M is equal to Z into I into T. Z into I into T. This is equation 4. Now see, what is Z here? Z is called electrochemical equivalent, a constant basically, electrochemical equivalent, and it is constant for given species, right? means if you have taken sodium, then Z is different for sodium. If you have taken potassium, then it is for potassium. It means it is specific for the given species. It is independent of any other factor, right? It depends on the nature of the species, right? So I is the current, and T is the time. So all of you are knowing the units and everything here. So how to define this Z? So if Q is equal to 1 coulombs or 1 ampere current for 1 second, then M is equal to Z. Then M is equal to Z. So now you can define electrochemical equivalent. So here you can define electrochemical equivalent. It is the mass of any species deposited by 1 coulombs of charge, 1 coulombs of charge, or 1 ampere current for 1 second, right? Provided that the current efficiency is 100%, means your electrical energy should not be lost in any form, right? In the form of heat or in any other form, in the form of resistance, there should be no loss in energy. So this is called current efficiency, right? So provided that, we can put here, provided that the current efficiency is equal to 100% for the cell. So this is the understood condition here. If nothing is mentioned, then it means we are considering 100% current efficiency. So electrochemical equivalent is defined as the mass of any species deposited by 1 coulombs of charge or 1 ampere current for 1 second, right? So suppose that if we are taking molten sodium chloride, molten NaCl, right? Molten NaCl, and if we see 1 ampere current, if we pass for what 1 second through this electrolytic solution, so how much of this sodium will deposit at the cathode, right? So suppose that you have to find out how much sodium, molten sodium chloride you have taken, inert electrode you have taken, and now find how much sodium plus deposit over cathode by 1 coulombs of charge, right? Suppose that this is the objective. So once you learn this, calculation. After that, you can apply for chloride ion and other similar ions. So first you have to write the equation. Na plus plus electron gives Na. Now see, apply the chemistry. Now tell me how to read this equation. Are you reading this 1 mole of Na plus or 1 sodium ion? Hmm? How to read this quantitatively, this equation? So the reading of this quantitatively, this equation is that 1 mole sodium ion. You cannot read this 1 sodium ion, right? This is 1 mole of sodium ion. Nothing is mentioned as in the equation. Then you have to consider each and every species with respect to 1 mole, not with respect to 1 atom or 1 molecule. So this is, if this is 1 mole of sodium, so you have to read like this. So you have to read this like 1 mole of electron. 1 mole of electron. You cannot read this 1 electron, right? And this is 1 mole of sodium. 1 mole. So you have to read this equation in terms of moles. So all of you are knowing that how much charge carried out by 1 mole of electron. So Q is equal to charge over 1 mole of electron, 1 mole of electron. So this is equal to 6.023 into 10 to the power 23 into 1.6 into 10 power minus 19 coulombs. So this is equal to 96500 coulombs per mole. Right? This is called Faraday's constant. This is called Faraday's constant. So you can write this is equal to F. Right? You can write this. So now from this equation, stoichiometry of this equation, we can say that 96500 coulombs of charge deposited sodium is equal to 1 mole is equal to 23 gram, right? 23 gram. Okay, so you can write 1 coulombs of charge deposits sodium is equal to 23 divided by 96500. Okay, got it? So this is very simple calculation. 23 divided by 96500. So it becomes equal to 0.00023 8 gram. So as per the definition, what is the electrochemical equivalent? What is the electrochemical equivalent? See, what is the definition of electrochemical equivalent? Electrochemical equivalent is the mass of any species deposited by 1 coulombs of charge. So here we have calculated sodium, how much sodium deposited over cathode by 1 coulomb. So 1 coulombs of charge deposited this gram of sodium ion. So you can say the electrochemical equivalent, equivalent equivalent for sodium or sodium plus, whatever it is asked. Sodium plus is equal to, because loss of one electron hardly matters, there is no change in the mass, 0.0000238. And what is the unit here? This is coulombs. So this grams per coulomb, right? This grams per coulomb. So 1 coulomb of charge will deposit this gram of sodium. So this is the electrochemical equivalent. But you can see this is very, difficult to use this value. So this is the reason why Faraday suggested his second law, and he introduced the concept of equivalence, because in equivalence there is some simplicity from this electrochemical equivalent, right? So this is the first law of what? Faraday. What is the first law? Mass of any species involved, mass of species on the respective electrode is directly proportional to the charge passed through the solution, right? So this is the first law. Now come to the second law. So in the first law you have learned about what is Faraday's first law and what is the concept of electrochemical equivalent. Remember the words electrochemical equivalent. It is the mass of any species deposited by 1 coulombs of charge. How much charge? 1 coulombs of charge. Okay. Now come to the second law. Second law. In the second law, see, suppose that we have taken two voltmeters, electrolytic cell also called voltmeter. So, and they are connected in series. They are connected in series. And we have taken different electrolytes. So, suppose that here electrolyte AB, and here we have taken C2 plus and D2 minus. Here A plus B minus. Means here I have taken univalent and here divalent. You can take one more in which univalent, divalent. You can take one more divalent, trivalent, whatsoever. That hardly matters. So I am taking only two. So what this law states, this law states that if you pass the equal charge through different electrolytic cells which are connected in series, then equal equivalents of all the species are involved at the respective electrode, irrespective of their valency, their oxidation state, or their charge. Whether they are divalent or monovalent or trivalent hardly matters, irrespective of all these things. The only criteria is current efficiency should be 100%. So if equal charge pass through different electrolytic solution, electrolytic solutions for electrolytic solutions connected in series connected in series, then equal equivalents of all the species involved at the respective right? And current efficiency should be 100%. Means there is no loss of energy in any other form, like heating, like resistance against resistance. Nothing should be lost. So you can write, by reading this statement, you can write here, and it is irrespective, independent of the nature of electrolytes, right? Nature means bivalent, trivalent, whatsoever the components of electrolyte, it is independent of that. So you can write here equivalent of A is equal to equivalent of B is equal to equivalence of C is equal to equivalence of D. And this equivalent is equal to, equivalent of A is equal to mass of A by equivalent mass of A. This is equal to mass of B by equivalent mass of B. This is equal to mass of C by equivalent mass of C. And this is equal to mass of D by equivalent mass of D. See, this is independent of their valency, their charge, etc. Right? Okay, so what is here? E. E is called chemical equivalence. Chemical equivalence. And it is defined as, this is the absolute definition of equivalent mass, right? Chemical equivalence or equivalent mass So whatsoever definition, whatsoever method all of you are knowing to calculate the equivalent mass, all have this, all are derived from this fundamental definition, right? What is the definition of this? Mass of any species deposited by 1 mole of electrons. 1 mole of electrons. And above we have calculated 1 mole of electron or 96500 coulombs or 1 Faraday of charge. Right? So this is the mass deposited by 1 mole of electron. So if you see the difference, suppose that again I am taking Na plus, so Na plus electron, this will give you the Na. So what is the equivalent mass? Equivalent mass of sodium or sodium ion is equal to the chemical equivalence. And this is equal to, see, this is 1 mole of electron, 1 mole, and this is the 1 mole. So 1 mole of sodium deposited by 1 mole of electron. So this is equal to 23 grams per equivalent. This is the unit of this equivalent mass, right? So see, this is equal to the atomic mass of this sodium. So for monovalent, it is equal to the atomic mass. Suppose that if you have taken diatomic like calcium 2 plus, so calcium 2 plus will give you the calcium. So 2 moles of electron deposited 1 mole of calcium. So 1 mole of electron deposit, that is the equivalent mass of calcium. So equivalent mass of calcium or calcium 2 plus is equal to 40 divided by 2. So this is 20 grams per equivalent. So this is the meaning of what? Chemical equivalents. So in this way you can define chemical equivalents and electrochemical equivalents. Electrochemical equivalents, see, for sodium, so this value 0.0000238, and here this is what 23 grams per equivalent. So this is the difference between these two. And the what is the limitation of this? Limitation is only that current efficiency should be 100%. So the current efficiency should be equal to 100%, right? So now you can find out the relation between electrochemical equivalent and chemical equivalent. So you simply use formula. So relation between Z electrochemical equivalent. Z is electrochemical equivalent and equivalent mass or chemical equivalent. So as you are knowing that 1 mole of electron means 96500 coulombs of charge deposited, the mass that is known as E as per the definition. See, mass of any species deposited by 1 mole of electron means 96500 coulombs of charge. Whatever mass deposited, that is the equivalent mass. And 1 coulombs of charge, suppose that 1 coulombs of charge, or suppose that not 1 coulombs of charge, uh, q coulombs of charge, suppose that we are passing, so it is unknown. For us, so let it be what W, or we can say 1 coulombs of charge, how much mass is deposited? Apply the unitary method. So equivalent mass by 96500, and by definition 1 coulombs of charge deposited the mass that is known as Z. So this is the relation between Z is equal to E by 96500. Right. So this this is the relation between Z and E, means equivalent mass. Very simple relation, and this is unitary method. Through unitary method you can prove this. Right. Clear? Okay, good. Now see, now I am going to give you one master formula for the all calculations based on this Faraday's law. See, milliequivalents of charge, because milliequivalents is so general formula, we can relate all units in terms of millikelvins, whether it is mass to mass, volume to mass, or normality, molarity, whatsoever, everything we can convert here. So milliequivalent of charge pass through the solution This is the master formula. Solution is equal to the milliequivalents of species deposited. Species deposited, right? So milliequivalents of charge, you can write Q by 96500 into 1000. So this is the milliequivalents of charge. If current and time is given, then you can replace Q is equal to I into T. This is equal to W by E into 1000. W by E into 1000. So this is the master formula, right? Mass of the, where this W is the mass of species deposited. And E is the equivalent mass of that species, chemical equivalent mass of that species, right? Now you can convert this. You can write this W is equal to area into thickness volume into density into 1000 by equivalent mass. See, this is equation 2. This equation you can use for electroplating. Electroplating of one article over other article. Usually we are doing this to protect the corrosion and other loss of the metal, and sometimes we are using this for aesthetic point of view, like for example if we can plate gold over silver, so it appears like this is gold. So electroplating, so what is area here? So first develop a little concept here for electroplating. In electroplating, what we are doing here, suppose that we want to plate gold over silver. So here you have to suppose that you have a silver spoon and you want to plate with gold. So make it cathode, right? And make this gold anode and silver cathode. If you want to plate gold over silver, right? And put some electrolyte having gold like 3+, right? You can take sodium argentocyanide or auric chloride. Basically, we are taking sodium argentocyanide. So now see this. What is area here? So area is the area of a spoon on which you want to coat or electroplate. So area. What is area here? Area is the area of article to be plated. Area of article to be plated. To be plated. Thickness is the, how much thick layer of gold you want to plate. Thickness is the, gold thickness here, gold thickness, gold metal thickness. So area into thickness, this gives you what? Volume, area, and into thickness. So this will give you the volume. Volume into density, this is the mass. So basically I have changed here in this formula. W is equal to, we can write area into thickness into density. So basically you can write like this. In place of W we can write this. And what is D here? D is the density, density of, D is the density of metal to be plated. To be plated, right? So here we have taken gold, so you have to take the density of gold. And what is E here? E is the equivalent mass of that metal to be plated. So E is the equivalent mass of metal to be plated. Right, so in this formula only the area you have to take the article to be plated, and density is the metal, density is the density of metal to be plated. No, this is the density of metal by which article to be plated, by which, D is the density of metal by which article to be plated, right? And E is the equivalent mass of metal by which equivalent mass of metal to be plated. Okay, no problem, metal to be plated, right? So this is another formula, and on this formula you will find many questions based on this, right? So this is the equation 2. Now we can make some more equations, but in a fresh form. Q by 96500 into 1000. This is equal to, now we can write here moles into n factor into 1000. This is equation 3. Here, what is this moles? Moles are the species deposited. Moles are the moles of the species deposited, right? And n factor of the species deposited. Species deposited. Now in place of moles you can take the volume of gas at STP, because sometimes gaseous species are evolved as a result of electrolysis. So you can use directly this formula. Don't convert first gram, moles, and then volume. You can use directly this formula. Moles of the gas, volume of the gas divided by 22.4. Unit should be careful. Liters, this is also in liters, into n factor of the gas into 1000. Right? n factor of the gas into 1000. So all these formulas you can use, but in all cases current efficiency should be 100%. But I am going to put here one note: if current efficiency current efficiency is given X%, then it is not 100%. Then what? How the formula is changed? Then you should change only in the left hand side. Then we can change the formula only in left hand side. What you have to take? Then in the left hand side you can take x by 100 into q by 96500 into 1000. Now this is the millicurrents of charge. Now see the electrolysis of water. Suppose that if we are taking electrolysis of water, one example. So water splits like this: H plus OH minus, and cathode reaction is H plus electron gives half H2, and anode reaction is OH minus. Either you can take OH minus gives 1/4 of O2 plus half H2O, right, plus electron, right. See the balancing, 1/2, 1/2, 1, 1/2, 1. Okay, now equation is balanced. Now see, by just writing this equation is balanced. Now you can find what is the equivalent mass of hydrogen. So equivalent mass of hydrogen you can write from here. This is 1 grams per equivalent. So one can question what, how you have calculated this equivalent mass. See here, see the equation: 1 mole of electron deposited half moles of hydrogen in this reaction. So this is the definition. That 1 mole of electron deposited how much quantity of any species, that is known as equivalent mass. So 1 mole of electron deposited half mole hydrogen. And see here in the anode reaction, 1 mole of electron deposited 1/4 mole of O2, right? So what is the equivalent mass of O2? The equivalent mass of O2 is equal to 1/4 mole. 1/4 into 32. This is equal to 8 grams per equivalent. right? So from here, basically, the concept of equivalent mass and chemical equivalence arises. So if you see, then each and everything whatsoever we are calculating in chemical calculations, mill equivalents, equivalents, everything is related to the 1 mole of electrons. All these equivalents, normality, balancing of equation, everything is related to this electron, right? Electron is the, I mean, key player of chemical reactions and chemical calculations. See, whatsoever the mass of any species involved with respect to 1 mole of electron, that is called what? Equivalent mass. So if you are able to identify that how much mass is deposited, how much mass is released by 1 mole of electron, then that is the equivalent mass. And the only way to write the partial ionic equation, but be careful that equation should be balanced, right? And you can balance this equation any manner. This value will not change. For example, if you are writing 2H plus 2 electron, suppose that if you are writing 2H plus 2 electron gives H2. So what is the problem? Here 2 moles of electron deposited 1 mole of hydrogen. So as per the definition, 1 mole of electron will deposit how much hydrogen? Same, right? So it is independent of equation, balancing of equation, whatsoever you are balancing, that hardly matters. For 1 mole of electron, this value is fixed, right? So in this way, you can, and what is the molar ratio of hydrogen and oxygen gas released in the electrolysis? Because sometime you will get direct questions on this. So hydrogen and oxygen molar ratio or volume ratio of hydrogen and oxygen in the electrolysis of water. So half mole, this is half mole, and this is 1/4 mole. So if you multiply here, so you will get 2 is to 1 molar ratio or volume ratio. Because you know, if all other things are constant, then mole is directly proportional to volume. So in the electrolysis of water, you will get hydrogen and oxygen in 2 is to 1 molar ratio, right? You will get hydrogen and oxygen in 2 is to 1 molar ratio, right? Okay. See this question. How much time is required for complete decomposition of 2 moles of water using the current of 2 ampere? So before going into the detail of solution of this question, answer of this question, first what information about current efficiency not given, so you take current efficiency 100%. If it is not given in the question, then you have to take 100%, right? Okay, now proceed. You can use this formula I into T by 96500 into 1000 is equal to moles of water decomposed into n factor for water into 1000. This formula you can directly, and you can solve this question in one statement, in one line, right? See this formula I am using. Moles into n factor into 1000 and Q by 96500 into 1000, right? So here current 2 ampere into time, they have asked T by 96500 into 1000 is equal to moles of water. They have given 2 moles of water into n factor for water is 2 into 1000. See how n factor is 2? See here. How many moles of water are deposited here per mole of electron? So here 1 mole of electron deposited half mole of water. So the equivalent mass of water is equal to 1 mole half mole. So half into 80. So this becomes is equal to 9 grams per equivalent, right? So the equivalent mass of water is 9 grams per equivalent, and all of you are knowing that n factor is equal to molar mass by equivalent mass. Equivalent mass, molar mass by equivalent mass, right? So n factor is 2 for water. Now you can simply solve this equation and get the answer. So T is equal to, you know, this is ampere, so you always get this in second. So unit you should be careful. T is equal to 96500 into 2. So 96500 into 2 is equal to 193,000 second. This is the answer. Now you can convert this into what? Minutes. 193,000 divided by 60. 3216, and one more 60 you can take. So this is 53.6. So this is equal to 53.61 hours. See, if you want the complete electrolysis, complete decomposition of 2 moles of water, so you are passing 2 ampere current, so this hours is required, right? See, this is the answer. Very simple questions, because this formula is so accurate and so shortcut, that if you see the solution in other books, you will find so long calculations. This is not required here, right? Okay.